Hello, everyone. So today I'm going to talk about a very important concept in linear systems theory called controllability. And I'm going to, what can I really do in an hour and a half? I can't give you a summary of the field. So what I thought I'd do instead is really drill down into a very important concept, as I said, the concept of controllability, and prove some very important results in the area. And just to give you a flavor of the kind of tools that are used in systems theory. And that's going to be the first 2/3 of the talk. Then the last third, we're going to apply those tools to a very specific problem and do a demonstration to show you the kind of novel things that you can do with that knowledge. And good. So before I start, I just want to get a rough idea who my audience is. How many folks here have background in electrical engineering? Okay, good. Quite a few. How about mechanical engineering? Okay, about half that. Computer science? Good. So it's about a third, a third, a third. So I suspect that most of you have seen what I'm going to present in one form or another today. I suspect, though, that most of you will not see the proof that I'm going to show you, because it's kind of a unique way of looking at things. And I'm quite certain that all of you, except maybe one or two students in my group, have seen the results that I'm going to talk about the last third of the class. So before starting, I want to give you a rough big picture view of people that do controls. How do they tackle problems? And what we find is a very useful way of breaking a problem up is if you have a system and it has some outputs, it has some inputs, and it's corrupted by noise or disturbances. One thing that we like to do, and the system, by the way, has a state X, has an internal state X, is that we build an observer that basically takes the measurements, takes the inputs that we apply to the system, and generates an estimate of the system internal state. Then once you have that description of that system internal state, okay, you have another system called a control, which takes the state estimate as an input. It takes some reference signal coming in, what you want to do, and from that produces the control input. Okay, this is a pretty standard way of breaking the problem up. It breaks down into two nice parts. There's the observer part, and this is what you would study in a recursive estimation class, a Kalman filter, a particle filter, a Bayesian filter, etc. And in terms of control, for example, this is what you would do in dynamic programming, where you assume you have perfect knowledge of the state when you come up with a strategy to control your system. Okay? Both of these are very deep and involved subjects, the observation part and the control part. Obviously, I can't talk about in details what this is about, but I do want to talk about a very important concept of, and specifically I'm going to talk about controllability, but it also applies to observers and observability. When can you actually reconstruct the state? And from this perspective, even if you knew the state perfectly, when can you actually drive the system to where you want to drive it? These are very fundamental questions. Okay. I'm going to do this development for linear systems, linear time invariant systems, and I have 4 reasons why I think this is important. Okay, so the first is, to first order, everything is linear. Okay, that's a tautology. By definition, I'm correct. You can't argue what I just said. To first order, everything is linear. Okay, but for control, there's a consistency thing that goes on there. Usually the task in control is to regulate something. So if you have a linear description for your system and you're doing a good job of control, your system will remain in the linear region, right? So the linear approximation is consistent with your objectives of what you want to do for control. So that's a nice tie-in. A lot of times, even though your problem may not be linear, you can convert it to a linear problem. You can do state transformations, you can do various manipulations to convert it to something that looks like a linear system. And the fourth is that a lot of advanced control techniques really have their basis, nonlinear control techniques have their basis in linear control problems. It's basically you take the technique that you develop for a linear system and you try to augment it to take nonlinearities into account. So it's basically a sound basis for anything that you do, but it's also extremely useful in its own right. Okay, so I'm going to talk about the concept of controllability for linear systems, linear time invariant systems. And so the system description that I'm going to have is a nice straightforward one. Okay, I'm going to assume that my state starts at 0. X is my state, U is my control input, and X of t, my state is an Rn, and my input U is an Rp, and usually P is less than N. Okay, this is what makes the problem interesting, is that you have less control inputs than you have number of states. For example, for something like this, a quadcopter, which I'm going to do a little bit of theory in the last part of the lecture, and we're going to do a demo later, has 12 states, right? It has 3 position, 3 orientations, and their derivatives that constitute the system state. So you have 12 states, and you have 4 control inputs, the thrusts of the 4 propellers. Okay, so the main question that you want to answer with controllability is, given a desired state that you want to achieve, is there a control input that gets you there? That's the basic question you want to ask. Okay, so given a desired state, how do I find an input that gets me to that state, if there is one? And if there isn't one, where can I go? And as we will see when I do this example later, you can then use that knowledge to figure out how can I design my system so that I can get to where I want to go. Okay, so the first thing we want to write down when we see an equation like this is, if we can, is to write down its solution. For this we can, because it's a relatively straightforward equation. We can find the solution is simply x of t is equal to the integral from 0 to t, e to the a, t minus tau, b, u of tau, d tau. So if you give me a control input u, I can solve for the state using this equation. And just a reminder, the matrix exponential e to the m is nothing but okay. So this is the matrix exponential, just keeps on going. Basically, it's just a generalization of the standard exponential, and we have to calculate this integral. Just keep in mind, of course, x is a vector, u is a vector, e to the a t minus tau is a matrix. Okay, so this is the solution. Simple check. You should always do when you see something like this, especially if it's straightforward to do. You can look at this and go, okay, is this? Am I convinced that this is the solution to this? Well, x dot x of t is equal to e to the a t, the integral from 0 to t, e to the minus a tau, b u of tau, d tau. So if I take the derivative, x of t, you have 2 terms with t, this term in the integral, this term here. Differentiate that, hold that constant, a e to the at, the integral from 0 to t, e to the minus a tau, b u of tau, d tau, plus, hold that constant, differentiate that. That's easy. This is the integral. This is the t there, so I just substitute e to the minus a t, b u of t. And of course, this is equal to a x of t plus b u of t. Okay, good. So simple sanity check. This is indeed the solution to this. Okay, so we want to formalize this definition of reachability that we can get to. Did I make an error? Yeah. X naught is equal to x0. Is 0. Thank you. X naught is equal to 0. So for all of this concept of controllability and reachability, we're going to assume that the starting state is 0. If the starting state is not 0, it gets a lot messier because we no longer are in a linear space. Okay? So I want to work with, as you will see, this definition of reachability, I really need to be in a linear space. You can generalize this when you have non-initial starting state, but for the basic concepts, you can assume that the initial starting state is equal to 0. Okay, so we want to formalize this definition of what is reachable, and there are three related concepts that I'm going to introduce. They're going to seem very, very different, and it turns out that they're all related. So there are three related concepts. Okay, and the first one is the actual thing that we care about, and it's the reachable space. So we define R of t, for a given time t greater than 0, we define R of t to be the set of all points that are reachable in a certain amount of time, t. So it's all xi in Rn such that there exists an u so that x of t is equal to xi. Right? So this is the set of all states that I can reach with some input u. And because this is a linear system and I'm starting at 0 initial state, it's very easy to see that this is a subspace of Rn. Okay. Yeah. It's the set of all x's for which, for any xi, you can find a u that drives me to that state. It's the set of all x's for any xi. Give me a xi. Is there a u that gets me there? Yes. That's for a different xi. There's a different u. Okay. All right. By the way, if you're not sure about something, please ask a question. And I do make errors, so case in point. So if you're not sure about something, or if you think I've made an error, please chime in. Okay. Okay. So this is the set of all reachable states. It's a linear space because we have a linear system, and I'm starting from state 0. And okay, so this is the thing that we care about, but it's not really that useful because how do I characterize what is reachable? Okay, this is basically just a definition. So for that, I'm going to introduce a second concept. 2. I'm going to take this matrix. I'm going to take matrices A and B, and I'm going to form a bigger matrix out of them. I'm going to call CAB, and it's just equal to B, AB, all the way to A n minus 1 B. Okay? And its dimensions are, well, it's easy. It has n rows. And columns, it's just equal to basically P. This is dimension P. Okay, and this is also dimension P, and I have n of them, so this is times np. Okay, so this is a thin matrix. It's a fat matrix. Okay, so it has many more columns than it has rows. Once I have this matrix, I can define the controllability subspace, CAB. So this is a definition. The controllability subspace is nothing but the image of CAB. Okay, which is equal to the set of all x's in Rn for which there exists a W in R and P such that xi is equal to CAB W. Okay, this is nothing but the definition of the image space of a matrix is nothing but take any, this is in the set, if you can find a W that when you multiply this matrix by W, you get xi. Okay. So that's the second concept I want to introduce. I'm not saying any relationship between 1 and 2. Let me introduce a third concept. Okay, the third concept is the controllability Gramian. And again, for a fixed time t, I define w of t to be the integral from 0 to t e to the a tau b times b transpose times e to the a transpose tau d tau. Okay, so this is a matrix. This is an n by n matrix, right? This is an n by p matrix multiplied by a p by n matrix. Integrate that out, I get an n by n symmetric matrix. Okay. So what's interesting about these definitions is that we have the following theorem, which is what I'm going to prove to you, is that RT is equal to CAB is equal to the image of WT. Okay? Yeah. It's fixed yes, this is the same t, and there is no t here. So I'm sorry, what your question was? So for any t, I get a subspace, or the reachable subspace at time t, right? And this theorem says that that's equal to the image of WT where t is defined as follows. So once you fix a t, it's fixed for this, but you can pick any t that you want. This relationship is satisfied. Okay. Okay, so we're going to prove this. We're going to prove this in a little clever way, which introduces some interesting techniques that people use in linear systems theory. I thought it would be interesting to expose you to it. But there's a couple of things that we can immediately say if we buy into this theorem. So the first is that this is a pretty easy check, right? It's just a matrix check. We just have to build this matrix and look at its image, and that tells us everywhere that we can go. So that's a nice computationally efficient way of figuring out what our space is. The second one is that this matrix here doesn't depend on time. There's no notion of time anywhere in here. That means that the reachable space is independent of time. It doesn't matter how small we make time, we can get to the space if we can get there at any time. So this is a bit of a surprising result, okay? The reason that you can really get away with it is because we have a continuous time system and you can scale time in any way that you want. For a discrete time system, it's a different story, but nonetheless, this is the result that we can state here. So to summarize, and I'll get back to this at the end, this result is very powerful because it allows us to easily characterize all the states that are reachable, and that's the connection between in here and here. And we're going to use this as a way to prove this, but this has an interesting interpretation of its own, and I will wait until I get there before I talk about it. So the way we're going to prove this is using a technique which is a very clever technique, and basically we're going to show that this set is a subset of this set, which is a subset. Okay? So we're going to show that this is a subset of that. We're going to show that this is a subset of image WT, and then we're going to show that the image of WT is a subset of RT. Okay? So it's a nice technique that's used. So to prove this directly without introducing this is difficult. By introducing this intermediate step, it becomes a lot simpler, okay, which is why we introduce it, but this also has an interesting interpretation in its own right. Okay, so in order to prove this result, we need a few preliminaries. These are standard results from matrix theory. I'm not going to spend a lot of time talking about them, but I will introduce them. And so preliminaries. So what we're going to do in the next little while is prove this. Okay, so just so that we know where we're going, we're going to prove this result. We need some preliminaries, and the first one is the Cayley-Hamilton theorem. How many of you have not seen this before? Okay, good. So I will spend time talking about it. It's a very nice result. So let rho of S equal to the determinant of Si minus A. So basically, we take our square matrix A, we do Si minus A, and we take its determinant. And I define this simply to be S to the n plus A n minus 1, S to the n minus 1, plus dot, 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 plus A0. This is also called the characteristic polynomial of this matrix A. The roots of rho of S are nothing but the eigenvalues of A. Okay, so right now I'm just defining this polynomial to be this characteristic polynomial. Then the Cayley-Hamilton theorem states that an plus little a n minus 1 a to the power of n minus 1 plus dot, dot, dot plus a0I is equal to 0. So this theorem, the Cayley-Hamilton theorem, states that any matrix satisfies its characteristic polynomial. Whenever you see a result like this, you should always look at special cases to make sure it makes sense. The simplest case, of course, is when this is just a scalar. So basically, the characteristic polynomial is simply S minus A. And if S, then A0 would just be A. Characteristic polynomial would be S minus A. And of course, if you put A in, A minus A is equal to 0, it trivially satisfies this. What's interesting about this result is that it works for the matrix case. The next simplest thing that you should check, the scalar is always what you check. Whenever you see a matrix equation, you should always check whether it's true for scalars. The next thing you should check is, can anybody tell me? Identity is not a bad idea, yeah? Diagonal, or diagonalizable. So diagonal is very close to scalar case. In fact, that's even better. I would check it for diagonal matrices. But more often than not, you can jump to diagonalizable matrices. So can we really quickly show this? Can we show this for diagonalizable matrices? Example, assume that we can write A is equal to T, some diagonal matrix T inverse. Okay, and of course, this diagonal matrix on the diagonal have all the eigenvalues of A. Then what happens when you substitute this in? Of course, you get T lambda T inverse times T lambda T inverse. Okay, so the T inverse times T's cancel out. And therefore, what you're left with is that rho of A. This is the short form of basically taking A and plugging it into this polynomial, is just equal to T, the characteristic polynomial, applied to lambda times T inverse, which is equal to T. And this is just lambda, the characteristic polynomial evaluated at lambda 1, characteristic polynomial evaluated at lambda 2, all the way to evaluated at lambda sub n times T inverse. By definition, these are the eigenvalues of matrix A. By definition, eigenvalues satisfy the characteristic polynomial, so this is equal to 0. Okay, so this is how you would have a simple proof for diagonal matrices. If for diagonalizable matrices, if they're not diagonalizable, then you have to go to something called a Jordan form. More involved proof, but again, the basic idea is this. Okay. So that's the first preliminary. We're going to need this. And just to give you some, always have some intuition of why we're introducing concepts. The reason that I want to have this result is that basically the fact that any matrix satisfies its characteristic polynomial is that A sub n can be written as a linear function of powers of A. Okay? And the reason that I care about that is that when I expand this out, we're going to see that higher powers of A can be expressed in lower powers of A. So it allows us to not worry about this infinite sum. It allows us to get some tractability there. Okay, so that's the first preliminary. Okay, then once we have the Cayley-Hamilton theorem, there's a simple proposition. And that is, let k is greater or equal to n, then there exists constants alpha sub I such that a to the power of k is equal to alpha 0I plus dot 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 plus alpha n minus 1 a to the n minus 1. Okay, very simple to show this. You would do it by recursion, okay, recursive proof. You basically prove it for k is equal to n, okay. Then you can just use the Cayley-Hamilton theorem because a sub n can be written exactly in that form. Then, given that it's true for a sub k, how do you prove it true for a to the k plus 1? Just write a to the k plus 1 as a times a to the k. You can expand a sub k out in terms of this way. So the highest power you're going to get is a to the n. Use this result again to express it in lower powers, and you get this result here. Okay, so proof by induction. I've been writing a lot of code the last month, so it's interesting. Instead of induction, I said recursion, but proof by induction. Okay, straightforward to do. Okay. So, and again, just to restate, the reason this is going to be very useful is that it allows me to simplify the matrix exponential. And once I have this proposition, here's the lemma that we wanted to work our way towards, is that there exists scalar functions phi 0 of t all the way to phi n minus 1 of t, such that e to the a t is equal to phi 0I plus phi 1 of t a plus dot 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 plus phi n minus 1 of t a to the n minus 1. Okay? And again, this follows pretty much immediately by substituting the definition of the matrix exponential, taking all higher powers of A that are higher than n, expressing them in this way, and collecting all the t terms, and you get the following thing here. We don't care what these functions are. Okay? You can easily work them out from the definition of the matrix exponential, but it turns out that it's not that important. Again, you should always do a simple sanity check. If A is a scalar, can someone tell me what these functions are? There's a non-unique way of expressing it, obviously. What's the simplest one? What's that? One way to figure it out, there's probably a, so this is phi 0 of t, right, times identity. How about this? Phi sub I is equal to 0. Phi sub 0 is equal to e to the at. What? Right, but I've just given you the answer right here. If A is a scalar, why not just pick all of these equal to 0? E to the at is just equal to e to the at. Yeah. All right. Well, exactly. If n is equal to 1, you just get this term here, right? And therefore, pick phi 0 is just equal to e to the at. Okay? It's trivial. I know it's trivial observation, but again, when you see a matrix equation that may look daunting, put in the scalar and it should make sense. Okay, good. So, Cayley-Hamilton theorem, nice result, allows us to express any higher powers of a as a sum of up to a(n minus 1), and we can use that to express the matrix exponential as a finite sum, linear sum of a to the 0 up to a to the n minus 1 for some functions. Okay, now that we have this, we're ready to start proving these three things. You're leaving for the proof. That's the best part. If you're going to stay for the preliminaries, you might as well stay for the proof. Okay. Okay, so we're going to prove step one. Step one is we're going to prove this here. Okay. So, how are we going to prove this? Take any element in here, and we're going to show that it has to be in here, right? Then that would suffice. That's what we're trying to prove. So let Xi be an element of this reachable space RT. So it's a state that we can reach given this time t, for which, so what does that mean? There exists a nu that will drive us to this state. Okay. Therefore, there exists u of t, there exists function of time u, such that Xi is equal to the integral from 0 to t, e to the a, t minus tau, b, u of tau, d tau. By definition, right? That's what it means for this to be in the reachable space. Okay. Now I am going to make the substitution of what e to the a t is. Therefore, Xi is equal to the integral from 0 to t, phi 0 of t minus tau, b u of tau d tau, plus dot dot dot, plus the integral from 0 to t, phi n minus 1, t minus tau, a to the n minus 1, b u of tau d tau. Did I make a mistake? Okay, I thought somebody was. Okay. All I've done is substitute that in here, and this is what I get. And I can easily write this as b, that's this term here, ab, all the way to an minus 1b, times, I'm not going to write this, but it's basically all of these integrals, right? The integral of phi 0 u of tau d tau. Second term would be the integral of phi 1 u of t minus tau u of tau d tau, all the way to the last term, which would be the integral of phi to the n minus 1 t minus tau u of tau. These are just scalars, right? Yeah. Okay, that's a very good question. So when I defined my reachable space, which I erased, okay, I just said that there exists a U that will drive me there. It turns out that, so the question is, well, you know, don't I need to put some restrictions on U to make sure that these integrals are well defined? Yes, you're absolutely correct. It turns out that they can be in L2, okay, and everything works out just fine. But that's a very good point, right? So, good student, that guy. Who is he? Whenever you see integrals, you got to make sure that everything is well defined, right? And for the purposes of everything that we talk about here, the U's can be in L2, right? So it's pretty much as nice functions as you can get of time. Okay, so therefore this is all well defined, and we're done because I've just shown that this can be written as b a to the n minus 1b times some vector, which by definition means that it has to be in here. Okay, so step one, pretty straightforward, made extensive use of the Cayley-Hamilton theorem. Okay, step two. Okay, we're going to show that the controllability subspace, which is nothing but the image of this matrix here, has to be a subspace, it has to be a subset of the image of W sub t, this controllability Gramian. Okay, now we're not going to show this directly. We're going to, again, do a little clever trick to simplify our proof. And for that, I need a basic definition. So recall that if I have a subspace S, then the orthogonal complement S perp is defined to be the set of all x's in Rn. So I'm assuming S is a subspace of Rn, all x in Rn, such that x transpose y is equal to 0 for all y in my subspace S. Okay, so this is the orthogonal complement of subspace S, just a definition, okay? It's also subspace. Then, with this definition, for any matrix W, I have the following result, is that the image of W, and I take the, so this is a subspace, and I take the orthogonal complement, this is equal to the kernel of W transpose. Okay. It's pretty easy to see that. I'm going to give you a one-line proof of that. If you have y is equal to WQ, and you have x transpose y is equal to 0, this implies that Q transpose W transpose x is equal to 0 for all Q, right? And the only way that Q transpose W transpose x can be 0 for all possible Q's is if the W transpose x is equal to 0, okay? Because Q has to be everything in the whole space. Okay, so that's the basic observation, but it's quite straightforward to see this directly. Okay, so why do we care about this? Because we're going to show, instead of showing that this is a subset of this, we're going to show that the orthogonal complement of this is a subset of the orthogonal complement of this. We will show, you know, if you want to show A implies B, that's the same thing as showing not B implies not A. Similar argument for sets. We will show that the orthogonal complement of AB contains the image of WT, the orthogonal complement of the image of WT, which by this statement here is just nothing but the kernel of WT transpose. But recall the definition of W sub T. It was a symmetric matrix, so this is just equal to the kernel of W sub T. Okay? So we're going to show this. We're going to show that the kernel of W sub T is a subset of the orthogonal complement of the controllability subspace CAB. So how are we going to do this? We're going to pick something that is in here and show that it has to be in here, as we did in all the other steps. Yep. Yes.
Do you use that direction for the reduction?
For what I'm going to do now, basically I am just taking this as a given result, and I'm just giving you some intuition of why that is.
So is it that direction that you use or the other direction?
Well, I need the equivalence of this. Oh, I see what you're saying. You're basically saying that all I really need here is that this is, that's correct. That's really all I need. But it turns out that this is equal, so it doesn't, right? But that's a good point. I actually need a weaker result in this. I just need that this is.
Because this strong result will not be true in infinite dimensions.
That's, yes, you're right. Right. It's a good that's a good point. Yeah. Everything here is finite dimensional, but that's a good point. Yeah, for this, you just need the weaker result. This is contained in here. Okay. Okay, so let's assume that I have Xc that's in the kernel. Let Xc be in the kernel of W sub T. So it simply means that W sub T times Xc is equal to 0, which certainly implies that Xc transpose WT Xc is equal to 0, right? Because this is equal to 0, therefore this is equal to 0. So therefore we can write that 0 is equal to the integral, substituting the definition of W sub T, the integral from 0 to T of Xc transpose e to the a tau b, b transpose e to the a transpose tau Xc d tau. Okay? And this is nothing but a signal times a the transpose of its signal. Okay. Now, if this is equal to 0 for all t, okay. So, well, first let me just define. Let y of tau equal to b transpose e to the a transpose tau times Xc. That's this term here. I've just shown you that the integral from 0 to tau of y transpose times y is equal to 0. And this I don't have to get into a complicated discussion because there's nothing smoother than the matrix exponential. If this is equal to 0, if the integral of y transpose y dt is equal to 0, then it has to be that y of tau is equal to 0 for all time. Okay? Because if it weren't, okay, then because this is such a nice smooth function, it has to be non-zero over a non-trivial interval, which means that you would get a positive result in the integral. Okay, so this is quite straightforward to show. Therefore, y of tau is equal to 0 for all 0 is less than or equal to tau is less than or equal to t. And if I have a function of time which is equal to 0, therefore all its derivatives have to be equal to 0. Therefore, the kth derivative of y transpose with respect to tau, evaluated at tau is equal to 0, has to be equal to 0. And from this you get Xc transpose a to the k b is equal to 0 for all k. just take the derivative of this, of y transpose, which is this thing here. Take the derivative, first derivative, you get a times this, then you get a squared, blah, blah, blah. You get this term over here. Okay? Good. So therefore, if this is equal to 0 for all k, I can rewrite this in matrix form. B, a, b, dot, 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 b, a, n minus 1b is equal to 0. I've just shown you that if xi is in the kernel of w sub t, then it also has to be in the kernel of, in the orthogonal complement of the controllability subspace, because this is equal to 0. Okay? That's it. We're done our proof. We've just shown that this is a subset of this is a subset of that, and this is a, no, I haven't shown that yet. I thought it was done. I'm not. One more step. We're almost there. So I still need to show this. Fortunately, this is very straightforward. In fact, everything so far has been pretty straightforward. All the steps are quite straightforward to follow. You know, of course, the hard part is coming up with a proof in the first place. The fact that it's nice and elegant actually just strengthens the result. Okay. So now we want to show the last part. And the nice thing about the last part is that it's constructive. Means that we can actually use it to drive a system to a given state. Okay. So let's see. Step 1, page 2, 3, 4, 1, 5, step 3. Okay. Step 3, I want to show that the image of W sub t is contained in my reachable space R sub t. So what I'm going to do is before, I'm going to pick something that is in here. Let xi equal to be an element in the image space of W sub t, which means nothing but that there exists a v such that xi is equal to wt times v, by definition what it means for it to be in the image space. And then define u of tau to be, that's not defined, just let it be, let u of tau equal to b transpose e to the a transpose t minus tau v in the interval 0 is less than or equal to tau is less than or equal to t. Remember, t is fixed, right? We're fixing t. And let's go ahead and substitute it into our state space equation, and we find that the solution, x of t, is equal to the integral from 0 to t, e to the a t minus tau, b, but now I have to put in what u of tau is, b transpose e to the a transpose t minus tau times v. d tau, which is nothing but wt times v, which is equal to xi, and we're done. We've just shown that if something is in here, I can find a u that gets me to that state, and by definition, that has to be in the reachable subspace. Okay? So, to summarize, we've shown that these three subspaces are the same. This is what we really cared about. We wanted to characterize all the states that we could get to given a certain amount of time t. We showed that there's a very nice computational test to determine what that subspace of Rn is. It's nothing but the image space of this matrix over here, which is very easy to calculate. And this result is nice because it tells us, it gives us a constructive way of coming up with a U that will drive us to the state. Okay? So if you want to get to a certain state in a certain given amount of time, here's a U that will do it. Okay? You first solve for V. If you can't solve for such a V, it means that you cannot get to the space. If you can, you solve for this V, you let U of tau be equal to this, and it will drive you to that state. What I really like about this result, and I don't have time to prove it, but for those that are interested, I can point you in the right direction. It turns out that this, out of all the U's, this is not unique, right? Out of all the U's that does the job, it is the one of minimum energy. It's the minimum energy. It has the smallest 2 norm out of all the U's that will drive you to that state. And the way you would prove that is you would define a controllability operator in the Hilbert space of L2, and you can come up and you can show that basically this thing that we created here is a projection. So basically, out of all the U's that drive you to the state, if you feed that through a projection, you will get this special U. So that's why it's the minimum energy. So this is a nice connection to all of this. Okay, so far I've given you a taste of some of the tools that we use in linear systems theory. Showed you a very fundamental proof in the area. This is pretty straightforward. This is pretty fundamental stuff, but you know, it's good stuff to build upon. I haven't talked at all about observability. I just don't have time to do it today. I thought I'd focus on controllability, but there are dual results for observability. Observability is a dual of controllability. There's a lot of nice, strong connections between the two. What I thought I'd do for the remainder of my time is show you how these tools can be used in a very pragmatic, practical way. Is Mark here? Okay, good. All right, so we're going to give a demo for you in a minute, but before we do that, let me erase the boards because I'm going to need them. Do we usually take a break or no? Okay, we'll go through. Okay. This is a quadcopter. It's a thing that flies. Many of you have seen these things fly either live or on the web or something like that. And you know, the basic way it flies is that it has these 4 propellers that generate thrust. And so you have 4 control inputs. But it's often better to think of these things as, instead of a simple control inputs, how do they work together? If they all speed up, so think about hover. You want to control this thing about hover. If they all basically produce the same amount of thrust, you have some equilibrium state. If you want to accelerate up, all of them increase their thrust. If you want to go down, they lower their thrust. If you want to roll the device, so if this is if I call this the x-axis, if I want to roll it, okay, I forgot to mention one important thing. These 2 propellers spin in one direction. These other 2 propellers spin in the other. These pitches have different orientations. These are clockwise propellers, these are counterclockwise. So these are spinning in one direction, these are spinning in the other, but they're all producing thrust going up. If I want this thing to roll, I speed this down, and I speed this up and I slow this down. Okay? The net thrust going up is the same, but it will create a moment that will want to make this thing roll. If I want to have this thing pitch, I do the same thing here. I speed this up, I slow this down. The net thrust remains the same. These guys are still producing the same amount of thrust, so the only torque produces in this direction. If I want to do yaw, I use the fact that when these things are generating thrust, the air is actually circulating, so there's drag involved. Now, because they're spinning in opposite directions, the net drag is 0 when it's just hovering, but if I speed these two up and I slow these two down, no net roll or pitch moment is created, but there's a yaw moment that's created. So you have these ways of affecting the system. Now, you guys understand this stuff. It's pretty obvious to you, especially if we just follow this lecture here, is that just because I only have 4 control inputs doesn't mean that I can only control a system with 4 states. This has 12 states, okay? 3 positions, 3 translational positions, 3 orientations, and their derivatives. So I have a total of 12 states, and I can completely control them with 4 actuators. Okay, so what I'm going to do first is I'm going to just write the basic equations of motion of this device, just so that we understand what the physics look like. And then we're going to analyze the flight of this quadcopter when it only has 2 propellers. Okay, so can this thing fly when it only has 2 propellers? And we're going to get some really nice results using basic tools from linear systems theory. Okay, so first, let's just come up with some equations. So quadcopter equations. Okay. So let's look at the translational dynamics. That's actually the easiest ones to write. Okay, you have this net thrust, and if I want to know where this thing is going to accelerate, I just have to know where this thing is pointing. If it's pointing in this direction, basically I have thrust being produced here, etc., whichever way it goes. So if I want to write down the net equations, the dynamics of this, I first have to rotate my vehicle. So if it's in this orientation, I need a rotation matrix that characterizes how I've rotated it to this specific orientation. That's just a rotation matrix. And I multiply that by the only net force that this thing can produce, the net force, which is just a thrust along here. So I basically have 0, 0A. But of course, I have gravity to contend with, minus G. Okay? So that's the translational motion. Very straightforward to write down. There's also drag terms here, which I'm going to omit. Okay, obviously, if this thing is flying, it's going to be subject to some drag, but I'm going to omit it for this analysis. Okay, so this is very straightforward to write down. All the magic is in this rotation matrix that characterizes the orientation of the quadcopter in inertial space. Well, I have a kinematic relationship between this rotation matrix, how this rotation matrix changes to the angular rates of the vehicle in its own frame. And I basically have this kinematic relationship, OVR dot, the rate of change of this orientation matrix is the orientation matrix relating the rates Okay, so omega sub x, omega sub y, and omega sub z are the rates in the vehicle frame. So omega sub z, omega sub x, and omega sub y. Okay, this orientation matrix relates. This rotation matrix relates these rates to the rate of change of this orientation matrix in the inertial frame. Okay, so this is a dynamics. This is nothing but a kinematic equation. But now I can write the dynamics, the rotational dynamics. And for that, I have J, omega x, omega y, omega sub z dot is equal to L F2 minus F4, L F3 minus F1, K F1 minus F2 plus F3 minus F4. I will talk about these in a minute. Minus omega cross J omega, where J is the mass moment of inertia matrix, which I'm assuming is diagonal. It's a good assumption for this vehicle. Okay? And what is this capturing? It's basically what I just said a little bit earlier, right? If I want this thing to roll, I just have F2 minus F4 gives me the difference that allows me to apply a moment. If I wanted to pitch, F3 minus F1 allows me to apply a moment. And if I wanted to yaw, I have to get all 4 of these things in the game to apply a moment without affecting the roll and the pitch. Okay. Plus, there's a drag term, which I'm going to omit for now, but I will need it later on. Okay? And the last thing that I need to write down is that MA is equal to F1 plus F2 plus F3 plus F4. That's this A term here. Okay? So you can see how these 4 thrusts allow me to produce a net thrust in translation and allow me to apply moments to change the orientation of the device. Now, good, I got enough time. Now, if I linearize, I want to linearize about hover. I want to analyze the system performance about hover. So if I want this thing to hover, I want to look at the equilibrium. And the equilibrium, of course, that all these derivatives are 0. All of these derivatives are 0. All of these derivatives are 0. And it's quite straightforward to see that for hover, you need hover equilibrium. You have that F1 bar is equal to F2 bar is equal to F3 bar. F4 bar is nothing but mg divided by 4. And the equilibrium orientation is just this thing being no roll or pitch angles. Okay? There's a yaw angle, but let's not worry too much about that. Okay? This is when these forces are all the same, all of these terms go to 0, means that there's no net torques applied on the device, and the fact that they all sum up to mg over 4 means that A is equal to g, and it exactly cancels out g here, which allows it to stay in equilibrium. Okay. So we want to analyze the system about equilibrium. So I'm going to take my Fi, and I'm going to map that to mg over 4, which is nothing but the equilibrium thrust, to Fi. Okay, so instead of defining a new variable, I'm just saying take my Fi's everywhere in here and substitute mg divided by 4 plus Fi. Okay? So Fi before was the total force, now it's the perturbation about the equilibrium. That way I don't have to define new variables. And similarly, I'm going to look at small angular deviations about hover. So I'm going to let OVR equal to 1 minus gamma, beta minus alpha, alpha minus gamma, beta and gamma. This is what a orientation matrix looks like when you have small angles. It's a small angle, small roll angle, small pitch angle, small yaw angle. Any rotation matrix that has small angles like that can be written in this way. So if you do that, your final equations that you get are x double dot is equal to g times beta. That's beta is the small pitch angle. Y double dot is equal to minus g alpha. Z double dot is equal to u sub z, which I will talk about in a minute. Alpha double dot is equal to u alpha. Beta double dot is equal to u beta. Gamma double dot is equal to u sub gamma. And what are these uz, u alpha, u beta, u gamma? It's basically solving a matrix equation which I'm not going to do. The terms here, 0 L over I xx, 0 minus L over I xx, and etc. I'm not going to write it down. It's basically just take these equations here, okay, and basically I want to just define these new control inputs. It's easier to write it in this way instead of keeping my original F's. I do a transformation. This is just a 4x4 matrix. It's invertible. Allows me to solve for the u's in terms of f's. Allows me to write the simple equations in this form. Okay, and this can be written S dot is equal to AS plus B sub U. S is 12-dimensional, U is 4-dimensional, and if you look at this, you can find that it's easily controllable. In fact, it's even stronger than being controllable. You can see that all the axes decouple when written in this way. Basically, the second derivative of x is equal to g times beta, but the second derivative of beta is equal to u beta. So one way to think about this is that the fourth derivative of x can be affected by control input u sub beta. The fourth derivative of y can be controlled via u sub alpha. Z double dot is controlled via uz, and gamma double dot is controlled via u gamma. Okay, so it's very intuitive. If you want to control the x direction, you first have to pitch the device. If you want to control it around y, you first have to roll it. Yaw can be done directly. Z can be done directly. Okay, so nice analysis. You can design a linear controller in this way, etc. Okay, but now we're going to do something a little bit more interesting. And this is going to serve the basis for it. Can we fly this quadcopter with only 2 propellers? And take me about 10 minutes to develop the theory, and then we'll do a demo to show that it's not just theory, we can actually do it. No pressure, Mark. So what I'm going to present now are results that Mark Muller developed as the lead author, and recently presented them at a conference, and we actually filed a couple of patents on this, which some folks, big quadcopter developers, are pretty interested in licensing. For reasons that I guess you can imagine, right? If you can fly a quadcopter with only 2 propellers, in fact, you can fly it with 3, Mark will demonstrate both, then you have a natural, algorithmic only way of doing redundancy. Instead of adding extra motors and propellers, you just have to have a clever algorithm that can handle flying with only 2 propellers or 3 propellers. Okay. So I'm going to show you a simplified analysis. There's a more complex analysis that we did, but a couple of things I want you to notice. When I want this thing to fly in space, the only thing I care about is the orientation of the normal. The actual yaw of the vehicle doesn't really matter. As long as the normal is pointing to where I want it to go, then I can fly it. So really this yaw, and in fact we saw from these equations, this yaw is just this extra thing that is just there. Of course, it's useful if you have a camera and you want to point it to people, but in terms of flying, this yaw is kind of redundant. It's not really necessary. So that's the first thing I want to state. Okay, now I'm going to talk about some assumptions. I'm going to assume, again, a reasonable assumption for a quadcopter that, and this just simplifies the analysis, is that Ix, x is equal to Iyy. Okay, so there's symmetry in this quadcopter. You know, it's a pretty good assumption. I mean, the battery is not exactly where, it's not an exact relationship, but it's close enough for this analysis. So, second, then I'm going to assume, I'm going to set which ones? I'm going to set F2 and F4 equal to 0, right? So basically, I can't produce thrust with these two propellers. So in these equations, I'm going to set F2 and F4 is equal to 0. You're going to see that now I only have 2 inputs instead of 4. So, and you can immediately see that I'm going to lose direct control of this omega sub x. Okay? And so let me write some of this down. So we're going to assume Ixx is equal to Iyy. Pretty reasonable. I'm going to set F1 is equal to, F2 is equal to F4 is equal to 0 for all time. So basically, I have no thrust in that direction. And I'm going to set F1 bar is equal to F2 bar is equal to mg over 2. So I'm going to see if I can have an equilibrium where I'm sitting here. And in order to do that, it's clear that I need to produce half the thrust with one propeller and the other half with the other propeller. I'm kind of jumping the steps of you know, you can deduce this through the equations, but I'm jumping to the conclusions to basically tell you that if you want an equilibrium, you need F1 is equal to F3 is equal to mg over 2. F3, yeah, okay. And then, so then I'm going to substitute F1 goes into F1 bar plus F1, F2, F2 bar plus, F3, F3 bar plus F3. And I'm going to redo this analysis with these perturbations here. One thing that I need, kind of missed this step over here. What happened to this guy here? Well, I was doing a linear analysis, right? So this was a quadratic term. So therefore, that's why I didn't include it in anything that I did here. Omega cross j omega is a second order term. For linear analysis, I don't need it. I'm going to include it here for a reason that will become obvious in a minute. Omega cross j omega is equal to omega y omega z times I zz minus I xx minus omega x omega z times I zz minus I xx and a 0. And the reason I get a 0 there is because Ixx is equal to Iyy. Then if I go ahead and write down my equations, differential equations, I get that omega sub x dot is equal to minus omega sub y, omega sub z, Izz minus Ixx divided by Ixx, omega sub y dot is going to be equal to u sub beta plus omega x omega sub z times this thing again. I don't want to write it down. And omega sub z dot is equal to k mg over Izz plus u sub gamma. Okay? And I'm going to stop there and just point something out to you. Well, I'm looking for an equilibrium here, right? So I want to look for an equilibrium where omega x dot is equal to 0. Well, that's okay because I have an omega y here. So if omega x and omega y are equal to 0, then omega x dot and omega y dot will be equal to 0. So I have an equilibrium here. This is my control input, right? But if I look at this, I just notice that there's a constant term here plus my control input, which is assumed to be small, right? I'm controlling it about this equilibrium. This could be large. That means that there's no way for me to have an equilibrium for omega sub z. And this is where I go back up here, okay? So I'm not going to look for an equilibrium where omega sub z is 0. I'm going to let omega sub z spin. Eventually, drag will limit how fast it can spin. So I'm going to include a drag term because I don't have an equilibrium about omega z is equal to 0. I could have one where omega x and omega y are 0 because of these cross terms, right? But omega sub z is not, it can never be 0. So I'm going to add a term here, which is nothing but the drag as a function of omega sub z, which kind of makes sense. If this thing is not rotating, there's not going to be much drag. The faster this thing spins, the more drag it's going to be subject to. The particular dependence of this doesn't really matter. All that really need to know is that when omega sub z increases, the drag increases as well. That's pretty reasonable. So now we can look for an equilibrium in the rotation rates. And one equilibrium is that omega sub x bar is equal to omega sub y bar is equal to 0. Okay, which is great because I have if this is omega y is equal to 0 and omega x is equal to 0, I will have the derivatives will be equal to 0. Again, remember, for equilibrium, my control inputs should be about this term should be 0. And omega sub z will not be equal to 0. How do I solve for it? Basically, I have omega z bar satisfies k mg over izz is equal to d at omega z bar. Okay? So eventually, the drag will be enough to overcome this term, and this thing will be spinning at a constant velocity. This u sub beta term and this u sub gamma term, it's the same thing as before. I can write a matrix equation that relates them. Minus L over Ixx. It's not important. It's just a simple matrix transformation. K over Izz. K over Izz times F1, F2 is equal to u sub beta and u sub gamma. Okay, that's what these control inputs are. They're just basically linear combinations of these F1 and F3. I just invert this matrix to solve for F1 and F3, and there I am. Okay, so now I have an equilibrium. The equilibrium is this thing standing still in space, but it's not just standing still rotationally wise, it's spinning about its yaw axis. And keep in mind that why are we okay with that is, remember, we don't really care about the rotation of this device. At the end of the day, we just care if we can point this thing in the right direction. So let's go ahead and do what we did earlier. We're going to let omega sub x go into omega sub x the equilibrium plus small perturbations. Omega sub y goes to omega sub y bar plus small perturbations. And if we do that, we get the following equations. Omega x dot is equal to minus a omega sub y. Omega sub y dot is equal to a omega x plus u sub beta. And omega sub z dot is equal to u gamma minus the derivative z bar dwz times omega sub z. We're not really going to care too much about this. This thing is spinning, whether it speeds up or slows down a little bit, we don't care. This is what we really care about. And what is this A? A is equal to I zz minus I xx over I xx times the equilibrium speed, rotation rate, wz bar. Okay, it's just simple substitutions. Okay, so we're almost there. What we care about, as I said, is the direction of the normal in inertial space if I want to control where this thing flies. Okay, so I want to be able to couple this analysis to how does my normal change as a function of omega x and omega sub y. I'm going to do that about equilibrium again. The equilibrium is that we want this thing to point straight up, so we want the normal to point straight up. And I'm going to do small perturbations of this normal about x, about this up orientation. Okay, so let n be the normal in inertial space. Nominally, n bar is equal to 0, 0, 1. Right? We want this thing to point straight up for equilibrium. We're going to look at perturbations around that and see how we can couple them together. So n is going to go into 0, 0, 1 plus small perturbations. And if I want to relate this inertial frame to my rotating frame, I just use my rotation rate minus omega cross n. Okay, so I'm assuming small perturbations around this normal that I want to point straight up, and the derivative of n is related to the n times the cross product of omega with n. Okay, so if I form this, I get that nx dot, ny dot, nz dot is equal to omega sub z bar ny minus omega y minus omega z bar nx plus omega sub x and 0. Okay, so now we're going to put this together. I have an equation here for omega sub x dot, omega sub y dot, and I have an equation here for nx dot and ny dot, and it depends on ny, nx, omega y, and omega x. Let's put all of that together. I want to make sure we leave enough time for Mark for his demo, so I'll wrap up in the next 2 minutes. Okay. Good. We put it all together, and we have the following equations. Omega sub x dot, omega sub y dot, nx dot, and y dot is equal to 0 minus a, 0, 0, a, 0, 0, 0, 0 minus 1, 0, omega z bar, 1, 0, minus omega z bar, 0, times the state, omega x, omega y, nx, and y, plus my control input, 0, 1, 0, 0, times u sub beta. Okay? So this is what we've been able to reduce the equations down to. Okay? Now we can apply the tools. Is this controllable? Okay, so we build CAB, build the controllability CAB. In this case, it's a square matrix, right? Because this is it has only one column. Therefore, CAB has is square. And if we want to check whether we can control the whole space, we just have to check whether it's non-singular, whether it has full rank, which is nothing but just checking the determinant. And if we build CAB and we look at the determinant of CAB, it's equal to minus A omega z bar, A minus omega z bar squared. Okay, so this is the punchline of this whole analysis. When is this determinant is equal to 0? Which is basically saying, when is my system not controllable? Two cases. A is equal to 0, not controllable. Right? Because CAB will not be the whole space. Well, what is A? A is equal to this. So we have this very nice result that basically tells us that if my mass moment of inertia about x is the same as my mass moment of inertia about z, I can't fly this thing. Okay? Not obvious at all. I mean, it's not, at least it's not obvious to me that that's the case. Okay? So this analysis immediately tells you that that's the case. And in fact, we could go even further and show that if A is equal to 0, the reachable space is equal to image 0, I3. Okay? So basically it's telling us that we can reach anything which is a linear combination of these three states, but it has to be a 0 here, which is kind of obvious. If A is equal to 0, there's nothing that could affect it. Okay? Great, but that's not it. There's another interesting case of when it's not controllable, and that's when A is equal to WZ bar. A is equal to WZ bar. But let's recall what A is. A is a function of WZ bar, and this implies, if you just equate A is equal to WZ bar up there, you get that IZZ is equal to IXX over 2, and in this case, the image space looks like 0, 1, 0, 0, 1, 0, 1, 0. Okay, so this is what you can actually control. This is the states that you can reach. It's not. It's two things that are uncontrollable, two dimensions. The subspace of uncontrollable is dimension 2. And what is this basically telling you is that you can't fly this thing if the mass moment of inertia about z is double that around x. And interestingly enough, for any planar body, this relationship holds. So this tells you that if you were to make a really flat quadcopter, so here it's not perfectly flat, but it's relatively flat, okay? It means that it makes it difficult to control. So this analysis, the beauty of this analysis is it tells you that for these two cases, okay, this thing can't fly. For when IZZ is equal to IXX, it can't fly, and when it's equal to this, it can't fly. So this analysis tells you how should you design this vehicle so that you can fly it. Okay, Mark, do you want to fly it? So this is a very simplified analysis of what actually goes into proving that this thing can fly. There's obviously the inertia of the motors that needs to be taken into account. That can readily be done. There's some higher order effects. So there's Mark taking the propellers off. Do you guys have insurance? So we've sacrificed control of yaw, but we still maintain control of the normal. And you may be wondering what those lights are. So I've only talked, yeah, go ahead and do 3. I've talked about controllability. There's a dual of it, observability. Just because we don't control the yaw doesn't mean that it's not important. We need to know where this thing is aimed so that we can go in the right spot. What we've done here is that we make this thing flash every time that it does one rotation so that the pilot can determine what the coordinate is reference frame with the vehicle's reference frame. So all of this analysis that I did was for what happens when 2 propellers fail. You can actually do it for when only 1 propeller fails, and you'll see a different equilibrium mode. Cool. Should I grab it? I don't trust myself. No, I'm not going to do it. Okay, great. And it turns out that theoretically we should be able to fly it with only 1 propeller, but again, if you use these tools and you do an analysis, it's going to be really hard. Okay, thanks.